Good morning, welcome to new lecture on random processes. So, in the last lecture what we discussed is we looked at the multiple random variables and we covered tons of density functions. We looked at joint probability density functions, we defined what is conditional probability density function. We understood what are statistically independent random variables, and towards the end of the lecture we also defined what is correlation and covariance. Today is going to be the last lecture in hopefully last lecture on random variables, and this is the outline of today's discussion. We will complete the discussion on covariance and look at the properties of covariance. We would then cover another important concept, that is random vectors, and finally we will look at derived distributions. So, this is what we have for you today. So, if you recall, so I am starting from covariance where we left in the last lecture. So, if you recall, we defined covariance of two random variables x and y as expected value of x y minus expected value of x into expected value of random variable y. Now, we discussed and derived this property in the last lecture. We also said that if x and y are statistically independent, then expected value of x y is nothing but it is the product of expected value of x into expected value of y. Okay. So, let us see what happens if the x y are statistically independent random variables, what happens to the covariance of those two random variables, and we will see something very interesting happening there. So, if you assume the two random variables to be statistically independent and compute its covariance, covariance by definition is this, and then we can simply substitute the expected value of x y if the two random variables are statistically independent. So, substituting this in this expression, what we get is something very interesting, that the covariance turned out to be 0. That means, if the two random variables are statistically independent, their covariance is 0, and if the covariance of the two random variables is 0, then we call them as uncorrelated random variables. If covariance is 0, then x and y are also referred to as uncorrelated random variables. Okay. So, I repeat, because these are very important concepts to understand, that if I have two statistically independent random variables, then their covariance always is 0, and if the covariance is 0, then you also call those random variables as uncorrelated random variables. Okay. Now, let me ask, if the covariance is 0, if covariance of two random variables is 0, of course, they are uncorrelated, but is it guaranteed that they are statistically independent, right? So, we have already shown that if they are statistically independent, if two random variables are statistically independent, they will be always uncorrelated, but if they are uncorrelated, is it guaranteed that they are statistically independent? So, to understand that, let me take this example where I have two statistically independent random variables x and z. So, the probability mass function of x is given to us, the probability mass function of z is also given to us, and what is also given to us is x and z are statistically independent, and I define another random variable u, which is nothing but the product of x and z. Let us find first what is the covariance of u with x. Okay. So, let us start. We have to find covariance of u and x, and by definition it is nothing but it is the expected value of u x minus expected value of u into expected value of x, right. So, let us compute first what is expected value of u. U by definition is x into z. So, this is expected value of x into expected value of z, because x and z are statistically independent and u is nothing but x times z. Now, if you look at the expected value of z, so if you look at z, where is its center of gravity? The center of gravity will be at 0. Okay. So, expected value of z is 0. So, what I will wind up with is expected value of u is also 0. Okay. So, the covariance of u and x reduces to expected value of u and x, because expected value of u is 0. Now, what is expected value of u and x? So, substituting for u, which is x z, what I get is expected value of x square z, and because x and z are statistically independent, I can write this as this, and I already know that the expected value of z is 0. So, expected value of u x is also 0, right. Hence, the covariance of u and x is 0. So, we can say that u and x are uncorrelated because the covariance is 0. Okay. Now, are u and x statistically independent? Let us explore. So, we have seen that u and x are uncorrelated, but the question that we have to think now is whether they are statistically independent. So, I have been given that u is x and z. Okay. So, how do I think about whether u and x are statistically independent? Let us go back to the definition. What I said about two statistically independent random variables, we said that if I give you some information about a random variable x, and if you do not learn anything about y, then the two random variables involved are statistically independent. So, in this case, suppose I give you information that x has taken a value 0. So, look at the PMF of x, x can take two values 0 and 1. So, if I say that x has taken a value 0, you know for sure that u must also be 0, right. So, these two random variables are not statistically independent. If I give you some information about x, you know for sure what the value for u would be. So, this u and x are not statistically independent, however, they are uncorrelated because covariance turned out to be 0. So, the big statement that we are making is if the two random variables are uncorrelated, they need not be statistically independent, but other way around is true. That means, if two random variables are statistically independent, they are guaranteed to be uncorrelated. Okay. Okay, so, let us now continue looking at the properties of covariances. So, first important property that we have to understand is, let me ask, what is covariance of x with x? Okay. So, let us use our definition. So, covariance of x with x is nothing but expected value of x into x minus expected value of x into expected value of x. So, this is by definition. So, if you look at this, this is nothing but expected value of x square minus expected value of x whole square, and this is nothing but it is the variance of x. Yes. So, we learn that covariance of x with x is nothing but it is the variance of x. Let us see what happens if I take covariance of x plus a and y plus b, where a and b are some constant. So, as we have seen in the case of the variance, what is variance? Let us revise. Variance, in variance we were interested in square of the distance from the mean. So, we had certain numerical values, we calculate the distance of those numerical values from the mean, we take the square of the distance and then we found the expected value. So, that was the variance of x, and we have said that the variance of x does not depend upon the constant. If you add a constant to a random variable, its variance remains unchanged, and covariance is also like variance. We are also interested in finding the expected value of square distances from the mean, hence the covariance is also unaffected by the DC constants. So, we can say that covariance of x plus a and y plus b is nothing but it is simply the covariance of x and y. That means the covariance remains unchanged with the addition of some DC constants. Let us see the third property of covariance. We are making a statement that covariance is a bilinear function. So, what I mean with this is, if you take covariance of a1 x1 plus a2 x2 with a3 x3 plus a4 x4, and this, because it is a bilinear function, you can write this as a1 times covariance of x1 x3. So, I am taking this with this. So, I will get a1 a3 plus a2 a4 covariance of x2 with x4, then a1 a4 covariance of x1 x4, what is left, x2 with x3. So, we have a2 a3 covariance of x2 with x3, right. So, covariance is a bilinear function. So, you can use this property, sometimes it will be very useful to compute the covariance. Okay. Let us make use of this property and see why is this so interesting. So, let us compute variance of a1 x1 plus a2 x2 up to am xm and see what it is. So, by definition this is nothing but it is the covariance of a1 x1 plus a2 x2 up to am xm with itself, right. So, it should be x1 a2 x2 up to am xm, and using the fact that covariance is a bilinear function, I can simplify this as a1 square into covariance of x1 with x1 plus a2 square into covariance of x2 with x2. You can go on like this, am square into covariance of xm with xm, and then there will be some cross terms. For example, a1 a2 into covariance of x1 with x2, then we will have a1 a3 covariance of x1 with x3 and so on and so forth, right. So, you can write this, you can write it compactly. This can all be reduced to summation a I square, where I goes from 1 to m, and covariance of x1 with x1 is nothing but is a variance. So, we can write variance of xi. Okay. So, we have collected all terms which have the same random variables. So, we can write all such terms compactly in this way. Then I have some cross terms. So, ai with aj, covariance of xi xj, where I and j goes from 1 to m, but I is not same as j, because I same as j has been already collected here. So, I can compact all these terms by using this expression. So, this helps us in computing some interesting quantities. For example, let us say if I am given that x1, x2 and xm are uncorrelated, right. So, I have said the variance of this, let me write it again, is nothing but is summation a I square variance of xi I going from 1 to m plus a I a j covariance of xi with xj I and j going from 1 to m and I is not same as j. Now, if I have been given that these are uncorrelated. So, random variables x1, x2 and xm are uncorrelated. If they are uncorrelated, their covariance, this term will go to 0. So, then you would end up with is just this term. Okay. So, this is how you can compute the variance of uncorrelated random variables. Of course, if they are statistically independent, then also they are uncorrelated. So, you can also use the same expression if the random variables that are given to us are statistically independent. Okay. Let us now look at another important concept, and that is about normalized variance, and we call this as correlation coefficient. Correlation coefficient is, first let me define this correlation coefficient. It is the covariance of x and y. So, I am defining the correlation coefficient for two random variables x and y. So, you have to first take the covariance of x and y, and then you have to divide this with square root of variance of x and variance of y, square root of variance of y. Now, something interesting that you would have noticed concerning the name. So, here we are taking the covariance, we are not taking the correlation, and still we are saying this as correlation coefficient. Last time also when we said two random variables are uncorrelated, we said that their covariance is 0, right. We said two random variables are uncorrelated if their covariance is 0, not their correlation. Here also we are defining correlation coefficient. So, it seems it should be in terms of correlation, but it is not. We are defining the correlation coefficient in terms of covariance. So, there is some inconsistency in the use of names of the quantities. So, let us see why is this so interesting quantity. Okay. So, let me, to simplify, let me assume that variance of x is sigma x square. So, square root of variance of x is sigma x and square root of variance of y is sigma y. Okay. So, I am defining rho as covariance of x and y divided by sigma x into sigma y. Okay. Now, let us assume that this rho is, let me expand this covariance of x and y as expected value of x minus mx into y minus my. So, this is by definition, this is the covariance of random variable x and y, and then we have in the denominator sigma x and sigma y. Remember, I have already introduced this notation of mx my. Mx is nothing but it is the expected value of random variable x, and my is the expected value of random variable y. So, this is the covariance of random variable x and y, and we have divided it with their standard deviation. So, square root of variance is also known as the standard deviation of the random variables. So, let me define A as x minus mx by sigma x, and let us define B as y minus my by sigma y. Okay. So, because x is a random variable, A is also a random variable and y is a random variable, B is also a random variable. So, I can write rho or correlation coefficient is nothing but it is the expected value of A into B. Okay. Now, you know in general expected value of A plus or minus B whole square is nothing but it is expected value of A square plus expected value of B square plus or minus 2 times expected value of A B. Okay. Now, let us see what is this expected value of A square. So, if I compute the expected value of A square, this turns out to be x minus mx whole square by sigma x square, and by definition expected value of x minus mx whole square is nothing but it is sigma x square. So, this quantity is 1. Similarly, expected value of B square is 1. Okay. So, I can write expected value of A plus or minus B whole square, expected value of A square is 1 plus expected value of B square is also 1 plus and minus 2 times expected value of A and B, 2 times expected value of A and B. And what is expected value of A and B? It is defined to be rho. All right. So, we get this as 2 plus minus 2 rho. Okay. Now, expected value of A plus minus B whole square can never be less than 0 because this quantity is always positive. So, I can say that 2 plus minus 2 rho is greater than or equals to 0 because this quantity is always non-negative. So, 2 plus minus 2 rho should also be non-negative. So, from this I get 1 plus minus rho is also always non-negative, and from this I can say 1 plus rho is greater than or equals to 0 and 1 minus rho should also be greater than or equals to 0. From this I can get rho is greater than equals to minus 1, from this I get rho should be less than 1. Okay. So, using these two I can say that rho always lie or correlation coefficient always lie between 1 and minus 1. All right. So, this is providing us some kind of normalized, this is some kind of a normalized metric because this values only lie between minus 1 and 1. So, if rho is 0, what can we say about this? If rho is 0, then x and y are uncorrelated. Rho 0 means the covariance of x and y is 0, that means x and y are uncorrelated. Rho 1 means what would be the meaning of rho equals to 1? That means x and y are highly correlated and it would be something like this. So, y will be a linear function of x where a is positive. So, if y is a linear function of x, the correlation coefficient between y and x would be 1. If rho equals to minus 1 would corresponds to the situation when y is again a linear function of x, but with a negative sign. So, the correlation coefficient between y and x would be minus 1 in this case. Okay. So, we have finished with everything that is important about covariance. let us now go to the next concept, and that is about random vectors. What is a random vector? A random vector is a vector whose elements are random variables. So, for example, this is a vector and elements of this random vector are random variables. Okay. So, just to introduce some notation here, normally if you are not given whether this is a column vector or a row vector, the vectors are assumed to be column vectors. That is normally the notation that is used in most books in digital communication. Vectors are somehow always assumed to be column vectors until and unless you are focusing on spatial topics in digital communication like error control coding, etc., where the vectors are normally assumed to be row vectors, but normally in other parts of digital communication the vectors are assumed to be column vectors. So, this is the same thing that we would follow. So, this is a column vector, x is a column vector, and normally because it consumes lot of space if you represent a column vector like this. So, vector is also a column vector is also written like this. So, you write it as a row vector and then you take a transpose, so that it is a column vector. This is more space efficient, and hence a column vector is mostly also represented like this. We will use this notation because it is easy to see that this is a column vector. Okay. So, now we have a random vector instead of a random variable, and things are how do we do certain operations on these random vectors. So, let me define expectation operation on a random vector x. So, x is now a random vector and not a variable. So, we are not using a different notation for random vectors, we are using the same notation, but I will like to stress always that this x is now a random vector. So, if I want to take the expectation of x, it is very simple. I can take the expectation element wise. So, I can take the expectation element wise okay. So, taking expectation is easy. Now, let us say that I am interested in random vector x minus expectation of x. What about this random vector? How do we think about this? So, it is simple that you subtract this also element wise, okay. So, this is how you should understand x minus expected value of x. So, you think about x element wise and subtract it from the expected value of each element. So, this is your vector x minus expected value of x. Can I add two vectors? So, what is the expected value of x plus y? So, remember these two are vectors, x and y are vectors. So, we can do or take the expected value also element wise. So, I am doing in one step because I hope that you have understood this. So, this is element x1, x2 and xm are elements of vector x, and y1, y2 and ym are the elements of vector y. I add these two elements x1 plus y1, x2 with y2, xm plus ym, and then I take the expectation element y. So, this would be the expected value of two random vectors x and y. Now, let me introduce something complicated, that is the variance of x. So, how do I think about variance? Variance of x we know is given by expected value of x into X transpose minus expected value of X into expected value of X transpose. Okay. So, we have already seen that variance of X can be given by this expression. Furthermore, what we assume is this random vector X is a 0 mean random vector, that means expected value of X is 0. And we make this assumption for two reasons. One reason is that it simplifies this expression, and second reason is noise is a random process with 0 mean, and thus the random vector obtained would also be with 0 mean. So, if I assume that the random vector is a 0 mean random vector, variance of that random vector simplifies to expected value of X into X transpose. And remember, this definition for variance applies if X is a column vector, and in this course we always assume the vectors to be column vectors. Okay. Now, let us first look into what is this quantity X into X transpose. So, if I have to find X into X transpose, X is x1, x2, let us assume up to m. So, I have m elements. So, this is m y1 vector, and X transpose would be x1, x2, xm. So, this is 1 by m vector, and then I have to multiply terms. Okay. So, then I will get x1 into x1, x1 x2, x1 xm, x2 x1, x2 x2, x2 xm, rest you can fill it yourself. Let me write the last row xm x1, xm x2, xm xm, and this is m by m matrix. Okay. Now, what we have to do is we have to take the expected value of this matrix, and we can do this by pulling this expectation operator inside this matrix, and we can calculate the expectation term wise. Okay. So, let us see what we end up with. So, we will get expected value of x1 square, expected value of x2 square, and so on and so forth, expected value of xm square, and you can fill in all these values. This would be expected value of x1 x2, this would be expected value of x1 xm, and so on and so forth. Rest I believe that you can fill yourself. Okay. So, now we have understood clearly, I guess there is no more ambiguity what I mean by taking a variance of a random vector x. What about the covariance? So, covariance of random vector x and y is also defined in a very similar way. It is expected value of x into y transpose minus expected value of x into expected value of y transpose. It is very similar, just you have to change x with a vector y. Okay. So, I have finished random vectors. They will be very useful when we talk about Gaussian processes or random processes later on. So, let us now look into another theme, and this theme is about derived distributions. So, what is the problem covered under this topic, derived distributions? The problem is that suppose you are given a random variable z, and this random variable is a linear combination of two random variables x and y, and suppose you have been given also that these x and y random variables are statistically independent, you have been given the probability density function of these random variables then the problem statement is what is the probability density function of this random variable z. So, what is the PDF of z? That is the problem. So, problem is to evaluate the probability density function of a random variable when you are given the probability density functions of some other random variables if this random variable is built using other random variables. So, this is the topic of discussion under derived distributions. This problem statement can be quite complicated, but here we are considering a simple case in which a random variable is just a linear combination of other random variables. Okay. So, we will be looking into just this problem at hand. So, let us get started. So, let us write again the problem that we have to solve. So, we have to find out the PDF of z in terms of PDF of x and y if x and y are statistically independent random variables. It is also often convenient to think about these random variables in terms of their numerical values. So, I know that numerical value of z would be a sum of numerical value of x and numerical value of random variable y. Also, assuming that this z is some constant, what I will end up with is an equation of a line which we can draw. So, suppose I have here the numerical values of random variable x, and on y axis I have a numerical values corresponding to random variable y. I can draw a line x plus y equals to z. For a given value of z, we can draw such a line. Now, to start thinking about the probability density functions of a random variable, it is often convenient to think it in terms of cumulative distribution function of a random variable. That means that if I want to evaluate PDF, it is often convenient to start thinking in terms of CDF, because we know that you can easily obtain PDF from CDF by just differentiating it with respect to a variable. So, in this case you can just differentiate the CDF of z with respect to z and you can obtain its PDF. And what is the CDF of a random variable? So, CDF of a random variable is by definition the probability that a random variable takes a value less than or equals to the numerical value in question. So, for example, if I want to find the CDF of random variable z at the numerical value z, it can be easily obtained by looking at the probabilities with which this random variable z takes in a value less than or equals to the numerical value z. And as we have already said, probabilities at a single point is 0, thus this quantity is same as evaluating this quantity Of course, if the probability density function is well behaved, meaning that it does not have any impulses and so on and so forth. Thus, whether I find the probability with which random variable z takes in a value less than or equals to z, or I just evaluate this probability, it is one and the same thing. Okay. So, what I am saying is I am interested in finding the CDF of z, which you can start thinking by thinking in terms of probabilities for which the random variable z takes in a value less than or equals to z. And how to think about this? We can think about this in terms of random variable x and y taking some numerical values, because that is what is given to us. Let me draw that line again. So, we had two random variables, we are plotting their numerical values. We said that I can draw a line x plus y equals to z. If I am interested in this quantity with what probability z takes in a value less than or equals to z, actually I am interested in all points that lie left to this line. And I can think about this probability of the points lying left to the line in terms of x taking certain values and y taking certain values. For example, I can rearrange this equation. Instead of thinking about this, I can write this equation, and I can ask this question in a different way. I can say, if I want to find the probability with which z takes in a value less than z, instead of thinking about this probability directly, can I think about the probabilities with which x takes in a value less than this, and that is the idea. So, I can freely choose my y, and for a given y I put the restriction that x should take in a value less than z minus y, where y is the value that I chose. So, let us formally state this. If I am interested in finding CDF of z, which is nothing but this, I can think about this in terms of joint probability density function of x and y, because a point lying to the left of this line will happen when y and x takes a particular values, and thus we have to think it in terms of joint PDF of x and y. And what I am saying is I can freely choose my y. So, y can lie between minus infinity to plus infinity, but for a chosen value of y, my x should be less than or equals to z minus y. That means, x can only lie between minus infinity to z minus y. And if you carry out this integration, you can find the cumulative distribution function of random variable z. Now, to simplify this thing, I can use the idea that these two random variables are statistically independent, and if two random variables are statistically independent, the joint PDF is nothing but it is the product of their marginal PDFs. So, instead of thinking about this quantity, I can think it in terms of this quantity, and then I can substitute this thing in here, and what I get is f z of z can be evaluated and using Fubini's theorem I can rearrange this integration in this way. All right. Now, the question is to obtain the probability density function. Now, probability density function of z can be obtained by differentiating the CDF. So, let us now differentiate this quantity with respect to z and let us see what we get. So, PDF of z can be obtained by differentiating integration that we had what you can appreciate is only this integration is a function of z, all these quantities are independent of z. So, while differentiating I need to just consider this part. So, let us think about this separately. So, let us see what we get if I differentiate this quantity. So, we get integration of PDF of x is the CDF of x. So, what we will get is this minus f x of minus infinity. Now, this quantity is 0. Why is this 0? Because it is giving me the probability with which x is less than minus infinity, and that probability should be 0. So, what I wind up with is simply this term, and this quantity is nothing but it is the PDF of x evaluated at z minus y. So, it is simple. So, what I get when I differentiate this integration with respect to z is simply and what is this? If you look at this carefully, this is nothing but it is the convolution of the probability density functions of x and y. Okay. So, what we have derived is if z is sum of two random variables x and y, if these two random variables are statistically independent, then I can obtain the probability density function of z by carrying out the convolution of probability density function of y and probability density function of x. And this is a very important result because it will help you in finding out the probability density function of a random variable in terms of probability density function of other random variables. So, let me show you a picture. So, let me assume that I have a random variable which is a uniformly distributed random variable, and I have summed up two such random variables. What I end up with is a density function like this. So, if you take a convolution of rectangle, you get a triangle. This is from the basic course in signals and system. So, I have a uniformly distributed probability density function, uniform within a range. So, you can assume it to be kind of a rectangle density function, and if you take the sum of two such random variables, independent random variables, the density of x will be the convolution of density of x1 and x2, and let us assume that they are identical random variables. So, the resultant density will be a triangle, like a triangle. And now if I add one more random variable, the density of that random variable will be the convolution of a rectangle with a triangle, and what you would get is such a shape. If you look at closely, this begins to approach a Gaussian PDF, and this is a very important insight. If you take random variables independent of each other, if you take a large sum of them, what you would get is the resultant density function would begin to approach Gaussian. This is not just particular to this example, but this holds universally, such that there is a theorem which is known as the central limit theorem, which says that if you take a sum of large number of independent random variables, the resultant probability density function begins to behave like a Gaussian probability density function, or it becomes Gaussian probability density function. So, this is a very important insight. This is a central limit theorem based on which we model noise even as Gaussian, because noise is nothing but it is a collection of many independent random phenomena. Okay. So, because we are talking so much about Gaussian, let us do that previous example, assuming that x and y are Gaussian. So, what is the resultant probability density function if x and y are Gaussian? So, I know that probability density function of z would be nothing but it is the convolution of probability density function of x, which if it is Gaussian would be like this. So, assuming the variance is sigma x square and mean is mx, convolution with the probability density function of y okay. So, I have taken the convolution of the probability density function of x with probability density function of y, and you can prove this. I leave it to you to prove that this is nothing but okay. So, what I get is the resultant probability density function of z, which is obtained by taking the convolution of the probability density function of x with the probability density function of y. This is the resultant probability density function. So, what you notice, that is very important result again. So, we are covering a lot of important stuff today, that the resultant probability density function is also Gaussian. So, I have taken a Gaussian random variable, I have taken another Gaussian random variable, both were statistically independent of each other. I sum them up, and what I end up with is the resultant random variable also is a Gaussian random variable, of course with a modified mean. So, mean has changed to mx plus my. So, mean of these two random variables have added, and the variance is sigma square plus sigma y square, where the variance of x is this and the variance of y is this. So, the mean have changed, the means have added, and as expected the variances have also added, and the random variable remained Gaussian, and this is also a very central result in digital communication course. So, let me make an important conclusion about what we have discussed so far, is that a linear combination of Gaussian random variables, these random variables, note, should be statistically independent. A linear combination of Gaussian random variables, the random variables which are statistically independent, is also Gaussian. Okay. So, this is this is very interesting, that if you take statistically independent Gaussian random variables, you sum them up, you make a linear combination out of them, and the resultant random variable is still a Gaussian. The density functions which shows this behavior are known as reproducible density functions, right. So, as you can imagine that there are not many density functions which are reproducible. So, it is a very special class of density functions which shows this property that you make a linear combination of density functions and the resultant random variable also exhibit the same density function, and Gaussian density function behaves in that way. So, important caution here is that Gaussian, we are making a linear combination of Gaussian random variables, but they are all statistically independent. If we have correlated Gaussian random variables, that means they are not statistically independent. If they are correlated, then the linear combination might not be Gaussian. Okay. This is important, it might not be Gaussian. Okay. So, do not think that if you sum up the Gaussian random variables, whatever they are, correlated, uncorrelated, the resultant is always Gaussian. It is not true. If they are statistically independent, yes, the resultant is Gaussian. If they are correlated, then we do not know. So, we have a special class of Gaussian random variables which are correlated, and still their linear combination gives a Gaussian function, and we will learn about such Gaussian random variables in the coming lectures, but in general this is not true. So, now we have seen two important properties of Gaussian random variables, that is a linear combination of a Gaussian random variable is also a Gaussian random variable, and before, if you remember, we have seen that a linear function of a Gaussian random variable is also a Gaussian random variable. So, these Gaussian densities and Gaussian functions are thus so important, and whenever we are in confusion how to model a particular phenomena, you better choose this to be a Gaussian function. Okay. So, we have in this lecture have seen several interesting properties of Gaussian functions, and we will see more interesting properties in next lecture. Thank you.